This week, while preparing for the show, I did something I don't think I've done before, and I did it twice. I was reading along, looking at new science from a variety of sources, and I realized two different papers had new discoveries that seemed to possibly fit together. So I wrote researchers and said, hey, have you seen this? Does it match what you're looking for? We are living at a time where advances in computing are allowing us to explore ideas faster than ever before. And with folks returning to campuses, we are starting to see cool new lab results again. And it all builds together. So today, I bring you lab results on ice that affects how we see the outer solar system and observations of galaxies that affect our understanding of the universe's formation. We go from things smaller than a proton, which we just learned is 0.73 femtometers across, to galaxy clusters, tens of millions of light years across. It's all tied together, and I'm going to tell you how. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. We'd like to start this episode off with a bang, or at least a future bang. A few years back, the Swift Observatory discovered soft gamma rays coming from a point on the sky where nothing particularly interesting had previously been noted. Follow-up observations with the SMARTS 1.5-meter telescope led by Noel Richardson identified a hot, massive star at the location of the gamma rays. Using a spectrometer, he hoped, with the help of a student, to get a handle on what was going on in the system. That student, Clarissa Paveo, found the system was a mess, a literal mess of stellar debris that was being heated by a star. This meant the spectra included lines from the hot debris and the hot star. Like a CSI agent with powerful computer tools, Paveo learned to write software to sort through the spectra, looking for the lines that only appeared in the star, and there was exactly one. In a plot of that line's wavelength over time, Paveo initially saw just noise, but Richardson's more experienced eyes let him see the orbital motion of a star around an invisible companion. Together, they were able to determine that their massive star was moving on a tight orbit every 60 days or so. Paveo recalls Richardson saying, "This is not just a simple binary system. This kind of an orbit could only mean one thing." As Jan Eldridge put it on Twitter, Richardson reached out to her saying, "Jan, we found this weird binary system with a neutron star in a circular orbit." That massive BE star wasn't the only big mass in the system, and in the past, it would have been the smaller of two massive stars. Eldridge is an expert in binary star evolution, and she and the team determined that once upon a time, this system had two massive stars, and as the larger of the two evolved, its companion was able to strip material off its expanded out surface. One day, that large star ran out of fissionable material in its core, and with no way to generate the light needed to support its structure, the star began the kind of collapse that normally leads to a powerful supernova. Except the material that would normally be in the star's outer atmosphere, the material that would drive the supernova blast as it crashed downward, it just wasn't there, and instead of exploding, the star kind of fizzled, with what did remain collapsing down into that neutron star we see today. That circular orbit Richardson saw, that was the key. A normal supernova would fling any remaining companion away, either completely or at least into an elliptical orbit. Circular orbits, however, are perfected when stars interact and share material back and forth. And the sharing isn't over. While that initial attempt to explode may have failed, this system is destined to one day merge in a golden kaboom. That remaining BE star that was observed is massive. As it evolves, it too will become a neutron star, creating a system with two tightly orbiting neutron stars that will radiate away energy through gravitational waves, until one day they actually merge through an event known as a kilonova. These super rare events create gold and other heavy elements. And when it goes, this system will fill its corner of our galaxy with heavy elements, as it screams out in gravitational waves and light. Sadly, we will not be here to report on that event. It will be at least another million years before the kilonova and merger probably happens. When we think of how our sky changes from night to night, the kinds of events we imagine are novae, moving objects, the changing moon. What we don't think about as often are the motions of the stars. But that may be about to change thanks to the amazing precision of the Gaia Space Observatory. Launched in 2014, Gaia is specifically designed to make high-precision measurements of the positions and brightnesses of stars, such that the tiny changes in perspective created by the Earth's orbital motion can be measured, and trigonometry can be used to map out the stars' locations. Its high-precision data also allows researchers to detect some stars' orbital motions. And with each passing year, we are able to get better and better data, describing both where stars are located and how they are moving around our galaxy. And the closer the star, the better the data. This has allowed one of the most interesting observations I've read about in a long time. Researchers studying the nearby white dwarf star, LOD 37, determined that it would appear to pass near a faint background star in late 2019. White dwarf stars are small and dense, and researchers realized that LOD 37's gravity should be able to bend the light from the background star such that we'd see the star in a slightly different place than normal. This kind of light bending scientifically is called gravitational lensing, and it was predicted by Albert Einstein and first detected by Arthur Stanley Eddington during a solar eclipse in 1919. During the eclipse, the positions of stars that appeared near the edge of the sun were slightly offset from where they appeared when the sun was in a different part of the sky. Until 2019, the sun was the only single star that had been seen to deflect the light of a background star. Nearly 100 years after Eddington took his photos, researchers led by Peter McGill observed LOD 37 using the Hubble Space Telescope and caught a new deflection. Thanks to Einstein, we know the amount the background star's position changed is directly related to the white dwarf star's mass. Working the equations, they found that LOD 37 has a mass of 0.56 solar masses. This measurement, which didn't require any major assumptions, allowed researchers to test models that describe white dwarf evolution and mass-to-radius ratios. Given enough time, more and more stars in our nearby universe may be caught in the act of moving the light of their far-off brethren as they orbit the galaxy. This is a first, and I hope it is just the start to a new way to measure stellar masses. gravity's ability to bend light is something we see a lot more when we look across vast distances. We can easily see how galaxy clusters bend light from the most distant galaxies, as they act like massive and imperfect lenses. What we see much less easily is how those exact same galaxy clusters are able to distort the light we receive from the cosmic microwave background. This light was emitted from everywhere when the universe cooled enough for neutral atoms to form. And we currently see a sphere of light that has been traveling toward us for nearly 14 billion years. This light has its path bent hither and yon by all the mass it passes, and careful computational analysis of our highest resolution images of the cosmic microwave background allow us to tease out where these distortions appear. In both cases, the lensing of distant galaxies and the lensing of more distant cosmic microwave background, the distortion corresponds to the amount of mass that exists to bend the light. And for one corner of the sky, a careful cross-correlation of how both the CMB and distant galaxies are lensed is now complete. The Dark Energy Survey and South Polar Telescope collaborations under the guidance of Timothy Abbott, C. Chang, Yuki Mori. Well, this team presents these results in a trio of papers in Physical Review D. The Dark Energy Survey measured galaxy clusters by the light of their stars and gas, and the South Pole Telescope and Planck Survey were used together to measure the galaxy cluster's distortion of the CMB. This combined approach provided the highest quality results to date and allowed them to compare our reality against predictions from theory. And as has been happening a lot lately, these high-quality results don't precisely match what was expected. And that is kind of exciting. It turns out our universe just isn't quite as clumpy as would be predicted. I can't tell you why or how, just that this is one more piece of evidence that our understanding of the universe, a lot like that gravitationally lensed light, still has a few kinks in it. We do science to explore, and I look forward to seeing how these new results help us find the things that went slightly sideways in our existing theories. After a short break, we're going to bring things back to the solar system and take a look at ICES, the icy moon Mimas, and that little helicopter on Mars, Ingenuity. Stay tuned. Scientists are driven by curiosity, and sometimes we just don't have the ability to do the exact experiments we'd like to do. This combination means we sometimes use data in entirely unintended ways to get at answers to our questions. Case in point, researchers led by the Space Science Institute's Mark Lemon used video of the Ingenuity helicopter to measure the properties of dust on Mars. When a helicopter takes off or lands, it can throw up clouds of dust. If it stirs up too much dust, it can cause a zero visibility brownout, making it difficult to navigate safely close to the ground. This brownout problem is why helicopter pilots try to avoid getting too close to the ground unless they can land on a helipad or other kind of solid surface. Sadly, the surface of Mars is lacking in helipads, and Ingenuity has to make do with what it has, which is basically one large dusty desert. Using videos and images from Mastcam Z on the Perseverance rover, researchers studied when and how dust was stirred up during Ingenuity's takeoff and landing, and while it traveled a few meters above the surface. Not all flights were exactly the same, which makes sense. Percy and Ginny are slowly meandering through Mars' Jezero crater, and they are experiencing a changing landscape. The team observed that Ingenuity sometimes kicked up dust when flying between points, but not always. As dust is not the best for any vehicle, flying higher may be in the helicopter's future. Unfortunately, what goes up and doesn't escape gravity does come down. And every time Ingenuity settled back to Mars' surface, dust was stirred up. In some cases, the wind from the rotors was enough to dislodge and break up aggregates of dust, which the researchers referred to as dust bunnies. I have to give kudos to this team for getting the term dust bunnies into their publication in JGR Planets. Using video to study dust is not ideal. The team basically looked for the differences between one frame in a video and the next. And by examining all of these differences, they were able to measure the movement of the dust very precisely. By knowing the air pressure, gravitational pull, and other environmental factors on Mars, they could calculate everything from the size of the dust particles to how much dust was being lifted into the air to which types of terrain appear dustier than others. This will allow mission planners to choose safer flight profiles in the future. This research doesn't mean we don't want to go plant dust sensors all over Mars and measure all these details directly. But this is a starting point, and this research will allow us to both better understand Mars and better understand how to keep little Ginny safe as she flies around for however long she manages to last. And we hope it is a good long time. Ingenuity was only meant to fly a handful of times during the first 30 days of Percy's mission. On April 3, she'll turn 2, which is really amazing. This research only used data from her first 6 flights, and I look forward to seeing future papers describing dust in more recently explored areas. As NASA plans future missions, we can expect to see more rotorcraft. The one many of us are eagerly awaiting is Dragonfly. Launching in 2026, this rotorcraft will arrive at Saturn's moon Titan in 2034. It is hoped the mission will explore dozens of sites as it explores the methane world's lakes, rivers, and thick atmosphere. From dust on Mars, we now turn to the many phases of water that may exist in the outer solar system. We know that Enceladus at Saturn has liquid inside because we see geysers. With other worlds, things are a bit harder to diagnose. Consider Saturn's moon, Mimas. With its one massive crater and myriad smaller surface features, this moon seems to be cosplaying as Star Wars' Death Star. The shape of that one massive crater, which is definitely not home to some worlds-destroying lasers. That crater's shape may be one piece of evidence for a stealth ocean. Here's what we know. The Cassini mission observed Mimas to have an oscillation in its rotation, scientifically called a libration, that we'd only expect to see from objects that are geologically active and able to support an internal ocean. And numerical simulations that work to recreate Mimas' surface features are consistent with thinning ice shells over a geologically young ocean. And, according to a new paper in Geophysical Research Letters, that is actually enough. That massive crater's name is Herschel, and according to lead author Adine Denton, quote, "We found that Herschel could not have formed in an ice shell at the present day thickness without obliterating the ice shell at the impact site. If Mimas has an ocean today, the ice shell has been thinning since the formation of Herschel, which could also explain the lack of features on Mimas. If Mimas is an emerging ocean world, that places important constraints on the formation, evolution, and habitability of all of the mid-sized moons of Saturn." End quote. This isn't the first time Denton found water where we didn't expect oceans to be. She is the same researcher whose models of Pluto were able to measure the thickness of its surface ice and possible liquid ocean as well. This evolving understanding of just where water seems to be is also forcing us to rethink the formation and history of these objects. Co-author Alyssa Redden puts it this way, quote, "Although our results support a present-day ocean within Mimas, it is challenging to reconcile the moon's orbital and geologic characteristics with our current understanding of its thermal orbital evolution. Evaluating Mimas's status as an ocean world would benchmark models of its formation and evolution. This would help us better understand Saturn's rings and mid-sized moons, as well as the prevalence of potentially habitable ocean moons, particularly at Uranus. Mimas is a compelling target for continued investigation." End quote. At this time, we don't have any planned missions to Saturn that could perform the much-desired observations. For now, all we have is a tantalizing possibility that water and life could be lurking just about anywhere. But if there was life in the water in this next story, it is now very dead. But really, it was lab water and it really shouldn't have had any life. I'm often amazed at the creative things people sometimes get to do in the name of science. Researchers at the University of College London and University of Cambridge discovered a new form of water ice by smashing up ice with steel balls at minus 200 degrees Celsius. Let me say that another way. Researchers cooled both water and steel milling balls down to minus 200 degrees Celsius, and they shook all of it violently. And the result of this low temperature smashing was crushed ice that had a different chemical structure than normal water ice. One of the super weird and periodically destructive characteristics of water is how it forms into a lower density crystalline matrix as it freezes at more human temperatures like 0 degrees Celsius or 32 degrees Fahrenheit. This means that the soda you forget in the freezer will explode, as well as uninsulated pipes on a particularly cold night. Most substances don't expand as they freeze. There are non-crystalline forms of ice, however, called amorphous ice, that have randomly oriented molecules. The highest density forms of amorphous ice form at temperatures below about minus 110 Celsius. And this form includes the kinds of ice that form on interstellar dust grains and that can play a role in the formation of the coldest icy objects in the outer solar system. These naturally forming kinds of amorphous ice are both denser than liquid water. This new form of ice that was created in the lab by crushing ice with metal balls, it's being called medium density amorphous ice, and it has about the same density as liquid water. Calling it a solid feels a bit disingenuous. The results of their very scientific smashing was a fine white powder that acted like water in a solid form. It is unknown if this form is naturally occurring, but our universe does a lot of smashing of ice at extremely low temperatures. And it is possible this kind of ice exists inside icy moons in the outer solar system. If it does exist, it could be responsible for some of the wildest geological activity out there. We know that when the denser forms of amorphous ice warm, the molecules will go from being randomly distributed to being in a normal crystalline structure. This change in structure is accompanied by a release of energy that makes icy objects puff out material and look temporarily like a comet. In the lab, the discoverers of medium density amorphous ice found that it also gave off a substantial amount of energy when warmed. And this kind of energy release could be responsible for tectonic motions like ice quakes on icy worlds like Ganymede. I have this terrible urge to run around asking ice researchers all sorts of questions now. Good, weird, creative research results do that. They change how we see things and give us new questions to ask. I will never know exactly what causes researchers to say, I'm going to freeze ice and ball bearings down to minus 200 degrees Celsius and shake. But I'm glad these folks do what they do. After the break, we're going to go from talking about molecules to talking about particles, as this episode takes a closer look at every size scale of the universe. Stay tuned. A lot of physics and astronomy is advanced one weird result at a time. And ultimately, to understand the largest aspects of our universe, we also need to understand interactions at the particle and molecular levels. To give you a for instance, earlier in the show, we talked about white dwarf stars. The physics for these was actually sorted out by one of the most brilliant astrophysicists, Chandrasekhar, while he was taking a boat from his home country, India, to Cambridge University to study for his PhD. This work that he did on a boat before graduate school would eventually play a role in his 1983 Nobel Prize and is now assigned as homework problems to physics and astronomy students. Yes, the maths that led to a Nobel Prize are now considered a good homework problem. Getting a physics and astronomy degree is weird. Anyways, in looking at how stars carefully balance the inward force of gravity against the outward force of light, Chandrasekhar realized that once a star died, once it used up all its fusionable material and stopped generating light through nuclear burning, whatever was left would collapse down until it was balanced between the outward pressure of the particles pushing against one another and gravity. This isn't too different from how a balloon is balanced between the elastic force of the plastic and the gas pressure pushing out. The thing is, the gas pressure in the core of a star doesn't follow the rules we learned in high school chemistry. Pressure isn't simply a relationship between the number of particles and their temperature. Instead, at sufficiently high densities, electrons start responding to each other and pushing outwards as they each take on a specific energy and spin. This is a product of that concept, the Pauli exclusion principle, which states that no two electrons can have the same energy level and spin value. In these stars, that energy comes from their motion, their kinetic energy. And the entire star ends up supported by the electron gas, essentially restricting what each electron can be doing and forcing them into a specific structure called an electron degenerate gas. Electrons are only so strong, however, and the force that allows two electrons to push one another apart can't support an infinite mass from collapsing further. It can't even support two solar masses of material from collapsing further. As Chandrasekhar would calculate, above 1.44 solar masses, gas can no longer support itself with just the repulsion of so many electrons. At this stage, electrons and protons will get pushed together to a critical point that allows them to merge together, release energy, and settle into the form of a neutron. This is why even larger stars become neutron stars. And it is why a white dwarf with its electron degenerate gas will be as big as the moon, while the more massive neutron star will crush down to the diameter of Manhattan Island. To understand the remnants of stars, we have to first understand in detail the physics of their particles. And thanks to a whole lot of experimental work over the past 130-ish years, we have a solid understanding of the stuff that makes up us and of what happens during a variety of atomic fission, fusion, and decay reactions. We can smash atoms together to build bigger atoms through fusion and better understand stars. We can put unstable variants of heavy elements like uranium into situations where it undergoes fission and generates energy, and get a better understanding of the naturally occurring fission that warms planets. We can even just watch as radioactive elements spontaneously decay. Our experiments brought us a detailed understanding of how we form and lose different atoms and what that means for stars, planets, and the universe as a whole. And in understanding how atoms can change, we've had to get a firm understanding of the particles that are generated and used up in all these different reactions. We know that the sun is blasting us with hard-to-detect neutrinos that are created alongside light in its core. We've come to understand that for every regular particle, there's an antimatter particle it will annihilate with. We have identified the forces that hold nuclei together, allow them to fall apart, and all the additional particles that are out there carrying these particle-affecting forces. This experimentally rooted model of particles is generally called the Standard Model. And it is a rock-solid piece of science that unfortunately can't be derived from first principles. There is no working theory that says, and then there will be these particles that we can observe, that doesn't also predict other particles that so far we have never been able to find. There is either something wrong with our approaches, or the universe has things in it that don't have fundamental explanations. Which is annoying, because we know there is undiscovered stuff out there. Dark matter, dark energy, inflation. These things require new physics to be figured out. And here is where we are stuck. Something caused the universe to balloon out in size during the first fractions of a second. We call that something inflation. Something is out there making up 27% of the mass that gravitationally yanks stuff around. We call that dark matter. And something is out there accelerating our universe apart. We call that dark energy. Whatever these three things are, these three things that define our universe and its evolution at the largest scales, these somethings have their roots in particle physics. When Plato recommended the truly educated should learn astronomy last, he was right. He just didn't know it was because you really need to understand particle physics, gas dynamics, and chemistry, both PChem and Orgo, to effectively do astronomy. So here we are, in a universe that it feels like we are so close to understanding. But we have these huge gaps. And not knowing something, that's just a motivation to work a lot harder for a lot of us scientists. And we are starting to look for new physics that will explain what we see at the largest scales while predicting what should be happening at the particle level. And whoever figures this out first, I suspect, is getting a Nobel Prize. And this week, we have a new paper vying for attention in the race for an answer. Publishing in Physics Letters B, researchers Florian Niederman and Martin Sloth describe a new way of looking at dark energy as something that can phase between states, like water going from a liquid to steam. In their model, they describe a universe that at some point in the first few 100,000 years, back before the release of the cosmic microwave background light, must have gone through essentially its own boiling process, as the stuff that is dark energy went from one phase to another. This idea is termed new early dark energy. And while physics requires cold dark matter, it apparently requires hot dark energy. Using this new non-constant form of dark energy, this team is able to derive an expansion rate of 17 kilometers per second per megaparsec from both early universe and modern universe perspectives. This removes the current tension between our different methods of measuring the expansion rate, which is called the Hubble constant. Coming up with a way to simultaneously understand dark energy and the expansion of the universe from different perspectives is compelling, but this team didn't stop there. They went on to describe additional ways that we should be able to see new early dark energy reflected in both the sky and our physics experiments. From their paper, we should also see variations in the large-scale structure of the universe. Interestingly, if I'm reading their paper correctly, we should see less clumpiness than expected. Although I don't know if this less clumpiness matches what we discussed earlier in the show. Further, we can expect to see specific kinds of particle physics reactions affecting leptons and the masses of neutrinos. There may also be a background of gravitational waves that will be detectable with future detectors. I hate saying this 2 weeks in a row about 2 totally different papers making totally different predictions, but I can't see any reason to think they aren't right. And I find myself rooting for them. So I guess I'm mostly just rooting for someone to please go out and prove that one of these new theories, rich in predictions, does or doesn't match the reality of our universe. What is really getting to me is how much neutrinos keep playing a role in all these theories. Neutrinos are hideous little particles that generally refuse to interact with anything, and they fly about the universe, changing their identity seemingly at a whim. This is not an exaggeration, except maybe the hideous part. I'm sure someone sees neutrinos as their darlings. As recently as 20 years ago, we didn't know if neutrinos have mass, and we didn't know why it seems that the sun's nuclear reactions produce far fewer detectable neutrinos than we expected. Every second, roughly 1 trillion neutrinos pass through your body. They do nothing. These particles interact so rarely that if a beam of neutrinos was shown through a light-year-long beam of lead, 50% of the neutrinos would just pass through and exit the other side. To detect neutrinos, scientists build vast chambers filled with liquids that they hope will give off the occasional flash of light to indicate something interacted with a neutrino. Different kinds of neutrinos interact in different circumstances. And in trying to understand the sun, we went looking for the kinds of neutrinos released when electrons are involved in the sun's nuclear reactions. And the number we found was too few. Once it was finally discovered that neutrinos have mass, it was realized that neutrinos could swap mass for energy and vice versa, thus transforming their identity, mass, and speed all at once, thanks to E equaling mc squared. This opened up a new way of looking at neutrinos, and modern theories allow space for a suite of neutrinos that could be used to explain what dark matter is, and would fit with this theory for dark energy and many others. As part of trying to study these antisocial particles that only interact via gravity and the electroweak force, researchers have developed ways to generate beams of neutrinos from sources here on Earth. One of these experiments is at Fermilab outside Chicago, and it involves generating muon neutrinos by firing protons at carbon atoms in a magnetic field. These neutrinos then hit a thin plastic target, and researchers watch for the flashes that indicate crashes. While this research hasn't yet changed our view on neutrinos, it has actually increased our understanding of protons. In a new paper in Nature, researchers led by Taejun Kao use the rare collision between neutrinos and hydrogen nuclei in the plastic to measure the size of the proton. While we knew protons have size, we couldn't accurately measure that size until now. That size is 0.73 femtometers, or 0.14 zeros 73. It's tiny. And we figured it out using data from an experiment not designed to measure atomic cores. And that is awesome. I don't know about you, but after all this cosmology and particle physics, my brain is now full. After a break, we're going to look at something less challenging: rocket launches. Stay tuned. One of our biggest challenges in space exploration is survival. And I'm not just talking about human survival. While the universe is certainly trying to kill us, it is also working mighty hard to destroy our spacecraft. From ionizing radiation to micrometeors to random high-energy protons, anything we put outside has to be prepared to get hit and radiated. In a lot of cases, we can just wrap things in many protective layers. Space capsules, space suits, space station modules. These are all many-layered things. Unfortunately, this kind of an approach doesn't work for protecting solar panels. Those have to be in sunlight and they have to work. The solar panels on the International Space Station have been regularly replaced and added to over the years, but in an ideal world, they would do their job without degrading over time. While the eternally working solar panel is still out of reach, researchers at the National Renewable Energy Laboratory have published a new paper in Nature Energy that describes how a micron-thin layer of silicon oxide could preserve the efficiency and increase the lifetime of perovskite solar cells in space. That 1 micron layer, well, for reference, one strand of hair is 100 microns thick. This super thin layer is 99% lower in weight than other barriers being used, and it is also not that expensive. While this doesn't give us eternally lasting solar panels, lower cost and lighter weight protection is definitely something we can use. So far, silicon oxide protective layers are only being used on perovskite solar cells in a lab. But it is hoped we'll soon see this technology not just making it into space, but also making it onto rooftops near you. In addition to protecting perovskite from radiation, it also protected it from moisture, which is mostly a ground-based problem. Solar panels aren't the only limiting factor on a spaceship. One of the harder to compensate for failure points is the spacecraft's engine. While still not functioning at a scale that could power a TIE fighter, ion engines are getting used in more and more spacecraft, such as Starlink's. These engines generate ions that bounce against the engine chamber and are magnetically accelerated out of the craft to generate thrust. This is a very, very low thrust kind of engine, but with constant firing, it will get the job done. Unfortunately, research finds that after very roughly 100 hours of firing, the ions will wear away 1 millimeter of the engine's ceramic discharge chamber. When too much of the chamber wall is gone, the engine will fail. We'd like to be able to accurately measure this decay. The problem is we are testing engines in vacuum chambers on Earth, which have walls. But we use engines in space, which space doesn't have walls. When ions bounce off the vacuum chamber's graphite walls, they sputter carbon atoms onto the engine being tested. To understand what is happening to the engine chamber, the material being sputtered onto it needs to be corrected for. Now, thanks to computational models by Hugh Tran at the University of Illinois, Urbana-Champaign, we can accurately understand how the engine and chamber are interacting. This is a computational triumph that combines molecular physics and careful laboratory techniques. And with new Starlinks getting launched nearly weekly, we'll be able to compare those lab results to reality in short order. Joining us next, in fact, is aerospace correspondent Eric Mattis, who has amazing SpaceX news that actually has nothing to do with Starlink.
Thanks, Pamela. This week was really a historic week for SpaceX, although it just might have been a traumatic day for a bunch of birds. Before I get to the big news, I have normal news from SpaceX, because SpaceX is a really busy launch company. SpaceX performed a commercial launch this week, sending Hispasat's Amazonas Nexus satellite into geostationary transfer orbit on February 7th. Amazonas Nexus is a high-throughput geostationary communications satellite that will serve all of the Americas and the North Atlantic corridor, along with Greenland. Built by Thales Alenia Space, it features both a Ku-band high-throughput payload and a Ka-band payload. It has a planned lifetime of at least 15 years. It also had a U.S. Space Force communications payload called Pathfinder 2, which is confusingly the third Pathfinder mission. It would have been the second Pathfinder mission had the launch of Amazonas Nexus not been one of the many satellites delayed by the COVID pandemic. Also this week, SpaceX completed the first 33-engine static fire of the first stage of the Starship rocket. This test has been anticipated for quite some time and follows many other static fire tests of fewer engines. These have ranged from spectacular, when one ended in a large explosion after a fuel leak, to a single engine firing furiously for a long time, which is rather underwhelming. Many of the tests have required engines to be replaced after the tests. That's not ideal, but it's important to remember that this system is still in early development. Because this was the first time all engines on the biggest rocket in the history of spaceflight were ignited at the same time, there was significant risk. The city of Brownsville closed the highway going to its beach, stretching 15 miles from the launch site for the entire day, and a 2.5-mile radius temporary flight restriction was established around the launch site to avoid hazards to aircraft during the test. The mission clock started the morning of the test at 8 a.m. local time. There were a few minor problems with the system during the day, which were not unexpected. Although it was planned for 33 engines, only 31 engines were lit. Of the two that didn't fire, one was commanded to turn off before the ignition, and the other did not start at all. As of the time we're recording this, the reasons for this have not been announced. To avoid ripping the rocket apart from vibrations, SpaceX staggered igniting the engines, igniting a few at a time until all 31 were lit over the span of about 6 seconds. After about 7 seconds from the initial ignition, the vehicle's computer smoothly shut down all engines, and after the dust cleared, it was still in one piece, and it appeared that the engines performed nominally. A short burn, but still the most thrust any rocket in history has produced. It seemed like every bird in Boca Chica took flight at that moment, and a massive cloud of smoke was produced when the 62 meganewtons of thrust was aimed directly at the bare concrete of the launch pad, with only relatively small streams of water to protect it. The legs of the launch stand were intact after the test, but definitely discolored. The process of draining the remaining propellant took place after the test, which took a while, but eventually SpaceX had a safe, intact rocket that is ready to conduct its inaugural orbital flight at some date in the future. After all that excitement, we still have to mention that Roscosmos conducted 2 orbital launches from Baikonur Cosmodrome in Kazakhstan this week. One was the Progress MS-22 resupply spacecraft headed to the ISS, while the other was a Proton M launch. Both launches were successful. And now for some statistics for a few of the things that are in orbit around the Earth. There are 9 toilets in space, 4 on the ISS, 2 on the Tiangong space station, 1 on the Shenzhou 14, 1 soon to be burned up on Soyuz MS-22, and 1 on Crew Dragon Freedom. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the US has had 11 launches, China 5, Kazakhstan 2, and Japan and the United Kingdom have both had 1. Of these 20 launches, there have been 2 failures, reminding us that space is hard.
Thanks, Eric. I was lucky enough to catch the SpaceX booster firing while it happened. And 33 engines sure make some mighty flame. Rockets like Starship and its mighty booster are going to revolutionize what we put into space. This means the backlog of wished-for missions may actually become a wealth of actual missions. One of the missions we've been waiting for is LISA, a mission that will allow us to start looking for new kinds of gravitational waves. We've been seeing plans for this mission since the 1990s, but it had been impossible to get the funding needed to see it launched until researchers could demonstrate that gravitational waves do actually exist and can actually be measured. That first measurement was announced on February 11th, 2016 by the US and European gravitational wave detectors, LIGO and Virgo. The actual detection had occurred on September 14th, 2015, but it took the collaborations time to convince themselves that this was it. This was the first real detection of the warping of space and time that is caused by gravitational waves. It is estimated that two black holes with masses of 29 and 36 solar masses had merged in a galaxy 1.3 billion light years away. This detection means you, me, and our entire world were squished and stretched ever so slightly, and a suite of giant detectors measured that change. Since then, more than 100 gravitational waves have been detected, and it now looks like the LISA mission just might get her day to fly. Currently, LISA is slated to launch in 2037 on a rocket to be determined. And when it happens, I hope to be here to report it. That's it for now. We'll be back next week with more science and rocketry. Good night, and remember to look up.